We're happy to have here today Michael Nielsen to give our distinguished colloquium of the quarter. Michael, I've known for a long time. I met him 10 years ago, actually, when I was a starting grad student. I went to visit his research group in the University of Queensland. Before that, he was an undergrad at the University of Queensland and then a grad student at the University of New Mexico. Was a postdoc at Los Alamos National Lab in Caltech, where he made important contributions to quantum information theory. And for those of you grad students who imagine that no one will read your dissertation, he turned his dissertation into a book together with Ike Chuang, which is pretty much the definitive textbook on quantum information. It's been cited close to 15,000 times, according to Google Scholar, and sold a lot of copies. So Michael, after went back to the University of Queensland to be a professor, led a large and successful research group. Many of his students have since gone on to become professors themselves. He then went to the Perimeter Institute in Canada to have a professor-like position there, and recently has left quantum information to do open science, which he's going to talk about today. He's just written a book about this, which is available now, although I'm not holding a copy. And he's going to tell us about topics related to new ways of doing science.
Thank you, Alan. All right, it's absolutely terrific to be here in Seattle. It's actually, it was the last time I was in Seattle, I was here for a day about 3 weeks ago, and before that, it was 13 years since I've been in Seattle, so I'm getting kind of a really nice dose and really enjoying it. As Aaron said, I'm going to talk about the idea of open science today, and I could start with a big abstract description of what this is, but I'd rather start with a story, just to explain the basic ideas. So the story begins with a mathematician named Tim Gowers. I should say, by the way, actually maybe I'll do a poll. How many people here would describe themselves as computer scientists? How many people would not? Okay, so a fair fraction of non-computer scientists. So I'm going to range all over. Some of my stories, well, they'll involve all sorts of different parts of science, not necessarily computer science all the time. I hope you'll see the applicability of some of the ideas I'll talk about, though, to computer science. So this one starts with a mathematician, this fellow, Timothy Gowers. He's a professor at Cambridge University and one of the world's leading mathematicians. He's a recipient of, among other honours, the Fields Medal, often called the Nobel Prize of Mathematics. Gowers is also a blogger. He's actually not that uncommon amongst leading mathematicians. Of the 42 living Fields medalists, 4 have in fact started blogs. So that's about 1 in 10. Just out of curiosity, how many people here have started a blog? Okay, so it's maybe about the same percentage as amongst the Fields medalists. I should say, by the way, 2 of them have abandoned their blogs, which is perhaps not that uncommon. So what Gowers proposed doing in this post, which comes from early 2009, the title is Massively Collaborative Mathematics Possible? And what he was proposing to do was attack a difficult, unsolved mathematical problem, a problem which he said he would love to solve, entirely in the open, using his blog to post his ideas and his partial progress. And what's more, he issued an open invitation inviting anybody in the world who thought that they had an idea to contribute to post that idea in the comments section of the blog. And his hope was that by combining the ideas of many minds in this way, it would be possible to make easy work of this hard mathematical problem. So he called this experiment the Polymath Project. Well, the Polymath Project actually got off to a very slow start. For the first 7 hours, not a single person wrote in with a suggestion. And then a mathematician from the University of British Columbia named Joseph Solomosi wrote a short comment. It's basically a simplification of the original problem, which he thought might give some insight, but was a little bit easier to get stuck into. And 15 minutes after that, a high school teacher, in fact, from Arizona named Jason Dyer made a short comment. And just 3 minutes after that, another mathematician, Terence Tao from UCLA, also actually a Fields medalist, made a comment. And things really were off and running at this point. The comments exploded. In fact, over the next 37 days, 27 different people would write 800 substantive mathematical comments containing 170,000 words. So I wasn't really a significant contributor to the project, but I was following along very closely right from the start. And it was really amazing to see what was going on. People would post a very half-baked kind of an idea, and then very rapidly, often, that idea would be developed, it would mutate, change into different forms. Sometimes it would be discarded. Gowers described the process as being to normal research as driving is to pushing a car. And at the end of the 37 days, he announced on his blog that the problem had most probably been solved. They still had to go back and check a whole bunch of details. They hadn't done a detailed verification. But ultimately, it turned out that, in fact, they had solved the problem, and they wrote a couple of papers describing their work on it. Now, of course, the reason I described this project, well, it's not important because it solved some particular mathematical problem. That's not why I'm bringing it up today. It's because it suggests that these kind of online tools can be used in some sense as cognitive tools. And by that I mean tools that amplify our collective intelligence. In other words, they help speed up the solution of some of the very hardest problems which challenge certainly some of the brightest people in the world. And perhaps it is possible that they can do this not just in a single area, but maybe broadly across many fields. And so that's the idea of open science or networked science, which I want to talk about today. So just to come back to the Polymath Project and more or less complete my story, of course, that was the very first iteration done in the first half or so of 2009. There have been many subsequent iterations. If you look at iterations involving essentially the same group of people, here's actually a list from the Polymath Wiki, which I actually maintain, of the existing Polymath projects. There's 9 so far that have been carried out with different levels of success, it must be said. They haven't all been as successful as the original. And an interesting fact is that in addition to these 9, there's maybe something like 5 or so more that have been done in other fields which are very similar. They don't necessarily call themselves Polymath projects. They range from fields like biology to computer science to astronomy. Exactly what this number, I've put approximately 5 here, it depends on what exactly you count. A really striking fact is that, in fact, some of these projects have been done by people who are completely unaware of this Polymath project. In fact, one which I'll talk about later was done by a group of amateurs some years before the first Polymath project. It maybe deserves to be called the first Polymath project. So this is a very similar pattern being used. In some sense, it's a pattern that's being discovered more than invented for collaboration. So in these projects, anywhere from a few people to on the order of 100 or so people have been involved. And as I said, they've ranged from extraordinary success through to outright failure. And of course, if you're doing real research, this is exactly as it should be. You shouldn't expect everything to work, and indeed it has not. So one of the reasons I think why there's maybe not been even more Polymath projects is because many of the people involved have gotten a little distracted. They've got involved in another very interesting thing that's going on within mathematics. And this is a website called Math Overflow, which I've shown here. And what it is it's a question and answer site for mathematicians. So basically, if you're a research level mathematician with a research level problem, you can go to the Math Overflow site and post that question on the site. I've actually chosen one of Gower's questions here just to illustrate the fact that some of the original polymaths are there, but there are many, many people involved. And this is, kind of it's not a bad example question. It's not as detailed as some. Can anyone give me a good example of 2 interestingly different ordinary cohomology theories? So this is not, please solve my undergraduate homework for me. It's at a slightly different level. Actually, if people do post those kinds of problems, they're quickly closed and kept off the site. So the last data I have available, this is not completely up to date, is that there's 2,500 users, about 30 questions per day, growing rapidly. 90% of those questions are answered within a day. In fact, many of the questions are answered much more rapidly. It's not that uncommon to see a question answered within a few minutes or a few hours. Several of the answers have appeared in research papers. When I said that it was research level problems, I don't mean they're not questions that you would write a paper about. They more tend to be of the nature, prove my lemma for me, or can anybody provide a counterexample to the following conjecture? That kind of level, sort of intermediate style results is not that uncommon. The way I like to think about it is that this kind of thing is in some sense a collaboration market. And it's not just for mathematics. In fact, the same pattern is being used in many different disciplines. Here's BioStar, which is essentially the same thing, but for biologists. There's many sites, several sites, in fact, for statisticians. Here's one of them. There's quite a few different sites of a similar nature being used within physics. Here's one. That's one actually aimed at theoretical physicists. And what's in common between all these sites and also with the original Polymath project is that in some sense they're taking expertise that we already have, that the human race already has, and they're activating that latent expertise. Or to put it another way, they're connecting the right expert to the right problem at the right time. Right? That's what's going on. So in some sense it's obviously true for the question and answer site. Somebody says, I have this lemma that I've spent a week trying to prove or disprove. They put it up on the site and then they connect to a person who says, oh, I know exactly how to do that. That's trivial for me because of my particular comparative advantage. But in fact, it's also true in the case of the Polymath project in a slightly different way. What's going on often there, you'll see the following pattern. Somebody will say, oh, here's my half-baked idea, and somebody else will say, oh, that makes me think of this idea. Somebody else will say, oh, that makes me think of, etc., etc., etc. Right? So they're stimulating each other with their different kinds of expertise. It's not unlike a good creative conversation, the sort that you might have in every day, but it's a little bit different as well. In some sense, it scales up the creative conversation. It gives more people an opportunity to leverage their particular talents and to insert them into the conversation. So you can find that person who serendipitously says, oh, I know how to, I know a counterexample to that conjecture, or I know how to solve your problem. So in some sense, what's in common, to sum this up, is that all these things, they're restructuring expert attention. They're redirecting people's attention. So instead of the participants in any of the sites sitting in their offices or at home, working as they usually do, they're using their expertise in higher leverage ways. So there's kind of a big, broad question here, which I'm going to finish this part of the talk with, and that is, how can we design tools which optimally allocate expert attention, which direct the expert attention in just the right way at the right time? And this question can be broken down. One, there's a technical problem, which is how to figure out how to allocate the attention where people have maximal comparative advantage. What should you be working on right now? Whose problem should you be helping solve, or who should be helping solve your problem? So that's a technical problem. There's also an incentive problem to go along with it, which is that it might be that somebody else should be helping you, that would be the optimal use of their time. But then even if they know that, they're not necessarily going to do it if they don't have the right incentives to do it. So you need to solve that problem. And in some sense, Polymath, Math Overflow, as well as lots of other tools, some of which you might have used, things like GitHub or IOC or Wikis or whatnot, are all really, you can view them as incomplete partial attempts to solve this problem of allocating expert attention. What should you be working on with your particular combination of expertise? And collectively, how should people be working? So I don't think this is, I want to say really it's a very fundamental question, in my opinion. It's a very basic question about the way we think collectively. And to illustrate it, I just want to use, actually it's a bit more than an analogy, but I'll describe it as an analogy. There's a very similar question, which is not about how we allocate expert attention, but rather how we allocate resources. So it might be commodities, it might be whatever. How do we allocate resources? And the answer to that question, all the tools and all the financial instruments and markets and whatnot which we use to answer it, determines the nature of our economy. And in some sense, the tools and the systems that we use to allocate our attention determines the nature of our collective intelligence. Okay, so I want to move to a very different aspect now of networked science. I want to talk about a site called Galaxy Zoo. How many people are familiar with Galaxy Zoo? Wow. Okay, that's... I've talked about Galaxy Zoo to many audiences. I think that's by far the largest percentage I've seen. Very interesting. Maybe. Okay, so what is Galaxy Zoo? Well, first, the obvious thing is it's a website, but the scientific purpose, it has a very good scientific purpose, is that in some sense it's a cosmological census. It was a site that was started in 2007 by a student and a postdoc at Oxford University. And what they had was they had a stack, a hard disk full of galaxy images, 930,000 from the Sloan Digital Sky Survey. So this is basically a robotic telescope in New Mexico, and so they have this robotic telescope scanning the sky night after night, takes lots and lots of images. That's fantastic, but when you have 1 million galaxy images, well, it's not so trivial necessarily to analyze all those images. In particular, it turns out that there are questions which computers are not very good at answering about that stack of things. I'll get to that in a second, actually. I should say that what they've been doing, what Galaxy Zoo does, is it recruits online volunteers to solve the following problem. This is the problem that, initially at least, they addressed, and it's a problem that people are better than computers at. So people will be shown a galaxy. I've shown 3 here. It's not so good, the image, unfortunately, but hopefully you can see it. And let's say they're shown this one in the middle, and they'll just be asked the question, is this a spiral or is this an elliptical galaxy? Very simple question. And the reason they're asked this question is, well, first of all, it's of fundamental significance for all sorts of reasons in cosmology, but kind of the proximate cause is that, in fact, humans supposedly are still better than the best computer algorithms at solving this kind of problem. So it's pretty easy in these cases, or it would be if you could see the images a little bit more clearly. But when you're looking at these sky surveys, the Sloan images, a lot of them they're just tiny little smudges. You can barely see a thing, right? It's right out at the limit of our ability to see, and it's kind of hard. It's not so obvious what you're doing. So people will be asked, is it a spiral or an elliptical? And in later iterations of Galaxy Zoo, they've been asked more complicated questions, things like, is it rotating clockwise or counterclockwise if it's a spiral? Is there a bar in the middle? These kinds of questions, all kinds of variations on that. They've recruited more than 250,000 volunteers, and they've done more than 150 million galaxy classifications. That's a lot of galaxy classifications. The way this project started was Kevin Shawinski, the student at Oxford, had sat down. He needed to test a hypothesis about spirals versus ellipticals, and so he classified 50,000 of the Sloan images in a week. Now, if you work 12 hours a day for 7 days, and you classify 50,000 galaxy images, that turns out to about once every 6 seconds you classify a galaxy image. You will not be surprised to learn that at the end of that week, he was a little bit sick of galaxy images. And of course, that's where this idea was born. Now, I want to give you a flavour of exactly what kind of things you can do when you have a system like this. So this is a question that was asked, or this is a galaxy that was seen by a Galaxy Zoo participant named Night Blizzard, or using the handle Night Blizzard. Presumably that's not their actual name. Very early on, in fact, about a month or so, I think, into the project, 2 months into the project. It was just this tiny little green splodge. You can ignore this. It's irrelevant. And they asked, it didn't look like anything that they'd seen before. It didn't look like a standard galaxy type, for reasons I'll get into in a second. So they went onto the Galaxy Zoo forum and just said, what type of galaxy is this? It's a bit weird. It's actually, he commented that it was very bright, unusually bright, and greener than he was used to. Anybody recognize it? Well, in fact, it turned out that it was not a type that anybody on the forum recognized. Well, over the next couple of months, several people in disconnected threads, the dots were not yet joined, found similar galaxies, same kind of basic thing. And they do the same thing. They'd post it and say, anybody recognize this? People would say, no, all kinds of different ideas about what it might be. And then something very fortunate happened. A Galaxy Zoo member named Tanny Van Arkel did something. It was a joke, and it was a very fortunate joke. She gave these little galaxies a name. She found one. It's down here, barely visible. And she called them a green pea galaxy and started a thread with the title, because it looks like a little green pea, and started a thread with the title, Give Peas a Chance. And this turned out actually to be a stroke of genius. The reason why is because it got them making pea jokes, the participants. So a whole bunch of people started to find similar types of galaxy. They would come in and they'd find a galaxy, and if they couldn't find a galaxy, they'd add another pea joke to the collection. My favourite is probably Peas Stop of all the pea jokes, indeed. But so this hunt for green peas started. And if you look today, several years later, there are now 20,000 posts in this hunt involving hundreds of people. It is in some sense, in fact, a Polymath project. What the participants did, at first, lots of jokes and good humour, but actually some of the participants, the more serious ones, gradually started to teach themselves more and more about the spectroscopy of these images. They started to develop a basic, the word theory is not quite right, but some basic understanding of what was going on with these green pea galaxies. First of all, they verified, with help from the professionals, that it was indeed a new type of galaxy. It's actually an extremely bright star-forming galaxy. So our Milky Way galaxy forms roughly something like 1 or 2 new stars every year on average. This galaxy is 10% the size of the Milky Way and is forming about 40 new stars every year. So much, much more rapid. They're very compact, as I already said. They're surrounded, this is a key signature, by very hot ionized oxygen. This was one of the first things that they determined, but it turned out to be a crucial signature, not actually something that is very common, apparently. They claim, I don't know enough. And they started doing ever more as they got more and more sophisticated criteria, they started doing sophisticated database queries to the Sloan Sky Server to find galaxies matching those queries. And so they developed a catalogue of these things. And finally, after much work, professional astronomers started to come in and they started to write papers about these things. There's actually a little, I guess, mini industry, it's fair to say, of papers on this. There's half a dozen or so papers about the green peas by several different groups. And I think particularly, if you're an amateur, which is what almost all of these people were, it's quite a remarkable thing to have done. You step back for a minute. They discovered an entirely new class of astrophysical object, which is pretty good for your summer vacation, I think, certainly for many of these people. More broadly, Galaxy Zoo has led so far to 22 scientific papers. And I'll just mention, this is sort of give you a profile of one of the leading Galaxy Zoo participants. This is taken from the Galaxy Zoo blog. It's a woman named Aida Berges. She's a 53-year-old grandmother of 2. She's from the Dominican Republic. She lives in Puerto Rico. She classified roughly 500 galaxies per week, plus many forum posts, plus she participates in several side projects, things like projects along the general lines of the green pea hunt. And she said of her participation that she first learnt of Galaxy Zoo from some publicity on CNN, and she said, and I quote, I went to Galaxy Zoo and my life changed forever. It was like coming home for me. Quite a remarkable experience for her. One of my favourite facts about them, among the many discoveries that she's been involved with, there are these stars that are going, we've got the Milky Way galaxy, and there's these stars called hypervelocity stars that are shooting very rapidly through the Milky Way. Most of the stars, like our Sun, are gravitationally bound to the Milky Way. These stars are moving so rapidly that they're not gravitationally bound, and eventually they will move off to infinity at some point in the far distant future. Well, the first of these stars was discovered, I think, around 2005 or so. There are now 20 known, and you've already seen my punchline, unfortunately, which is that she discovered 2 of the 20 or so known hypervelocity stars. Pretty good. So, just to sum up this point of view that I've been developing here, in some sense, this should not, by the way, this is not the right way of thinking about the relationship between the scientific community and society as a whole. They should not be separate. But for the purposes of illustration, I want to separate them out. And we have all these interesting bridging institutions between the two. So Galaxy Zoo, this kind of citizen science project, is an example of a bridging institution. It's causing a relationship between the scientific community and society as a whole. And I think it's fair to say it's an unprecedented relationship, certainly on this scale. Been much citizen science before, of course, going back hundreds of years, but getting 250,000 people involved in one project, that's a bit new. Now, how in general, what sort of, I want to ask the question, what sort of bridging institutions do we have between the scientific community and society as a whole? Well, traditionally, we've had a few. Obviously, the education system, including the university system, is of course an example of such a bridging institution. There's a whole community of people who do science outreach and science communication. They're creating things like documentaries and these kinds of projects. There is a pipeline from the scientific community, both into companies, of course, through engineering and whatnot, and also into policy, all kinds of senior technocrats in the government. So those are a few ways which we bridge, but I think one of the interesting things about these network tools is that they actually are creating the opportunity for several new types of bridging institutions. So not just citizen science, but the open access journals which have been created and open access repositories are also an example of a new type of bridging institution. There's science blogging, there's science news sites, and potentially many other kinds. It's very early days. One of the interesting things about Galaxy Zoo is that, so it was launched in May of 2007. It was launched with a budget of essentially, well, to first order $0 on borrowed money. They kind of twisted the arms of some friends who were web developers to help them out. So, sort of chutzpah and imagination were what they were running on. And I don't think anybody anticipated that it would explode in quite the way that it has. So it's difficult to say how much further is this kind of thing going to expand. It is the very early days, and it's very interesting. So what I think is interesting, the whole point of this, is that when you start to build new institutions that bridge these two communities and that are still very rapidly growing and whose limits are not yet known, that's a really interesting situation. It's those kind of institutions which can change the relationship between science and the rest of society. And I think that's a really interesting possibility and one that we haven't yet adequately explored. It'll be interesting to see what happens over the next 10 or 15 years. So just to sum up that first half of the talk, I've said that network science can speed up the process of discovery and can potentially help change the relationship between science and the rest of society. So it's a very upbeat kind of a way to start. The second half of my talk will be much more pessimistic, or for the most part anyway. I just want to talk about some of the ways in which scientists have been inhibited in adopting many of these tools. Yeah.
So I was curious if you would comment on what you see as different and interesting about this approach versus, the secondary effects that things like the space race did, where it encouraged people to get excited about science, to become engineers, to want to be part of those kinds of projects.
Okay, so it's an interesting question. Few things. That has a very complicated answer, but to get started on an answer, I think it's a great question. One thing is that there are middle schoolers and high school students who are involved in Galaxy Zoo, and they're never going to become scientists. They're not interested in going and becoming scientists, and that's actually a good thing, right? What it means is that there are kids in schools out in the middle of nowhere who are getting an experience, not just of what science is about. They're not seeing it on television. They're not seeing a rocket going to the moon, as exciting as that may be. They're doing science, right? And they'll carry that experience with them for the rest of their lives. And that's a very profound thing, and I think very different from seeing it on television, right? I grew up in Brisbane, which is a big city in Australia, a couple of million people. And the first time I met a scientist was when I was 16. I kind of had a youth of intellectual privilege compared with 98% of people in the world, and I expect that most people in the world don't grow up knowing any scientists. That's probably not true of many people in this room, but that's because it's a very self-selected group. And so providing opportunities for people who, stay-at-home grandmothers of two to actually participate meaningfully in scientific projects, that's changing who can actually be involved. That's potentially more important than any particular scientific impact. So there you go. Okay, so I want to talk about the downside. I want to talk about this pessimistic story about inhibition. So I'm going to start again with an example, as I did the first half of the talk. I'm going to start with an example. It's a website called the Wiki. It was started in August of 2005 by a grad student at Caltech named John Stockton. He announced it at a workshop in August of 2005. And the idea, as you can perhaps guess from the name, it stands for Quantum Wiki. And it was to be a kind of research-level Wikipedia-style site, a wiki for quantum computing. The intent, in some sense, was to create almost a super textbook for the field. So it would be very rapidly updated with news about the latest advances, with descriptions of the big open problems in the field, people's discussion of their ideas about how to solve the problems, descriptions of what was going on in the labs that are at the forefront, all these kinds of things. That was the general idea. And it was very interesting to talk to people at the workshop about their impressions. So quite a few were outright hostile. They'd be like, yeah, this is a stupid idea, who's ever going to do this? But a large group of people, certainly many people I talked to, were very enthusiastic. They'd say, oh, you could use it to do this, you could use it to do that, had all these ideas. So we'd talk for a few minutes, and I'd say, well, so what are you planning to contribute? Oh, no. I don't have time. But I really hope somebody else will take the time to do these kinds of things, right? Yeah, so they wanted the site to succeed. They thought it would be a tremendous resource. They could see all sorts of things to do with it, but they didn't want to take the time themselves to contribute. And of course, if that's the case, then the idea of a collaboratively constructed super textbook is not going to go very far. And I think it's fair to say that overall it has failed. And in fact, this is a pattern that's been repeated many times. It's very easy to find science wikis with similar ambitions. I should say, if you use them for different purposes, you can have successes. But for this particular style of science wiki, that have repeatedly failed. I should perhaps I want to clarify one other thing. They are not necessarily failures when you judge in terms of number of downloads, number of people using the site, these kinds of things. I've talked to some of the site owners, and very often there's loads of people looking at the site, but nobody actually contributing, right? It's this very dramatic asymmetry. Okay, same thing is true in many other areas. The string theory wiki, the person who created that said almost exactly the same pattern. Another set of tools which seem very promising a priori, the scientific social networks, what many people describe as the Facebook for scientists, the idea of making it possible, or making it easy for scientists to connect to other scientists with complementary interests so they can share ideas, share code, share data. And there have been many sites along these lines created, often very well funded with all sorts of institutional backing. I've just shown a few up here. And I've created accounts on many of the sites. You log in, you look around, and you discover that you're in this virtual ghost town. There's very often not a single person there that you can find, or very few people there. Actually, there's a bit of a rule of thumb. Very often, you find somebody, you look at the name, and you discover that it's the person who created the site, which is not so great. They'll often say, this one you can't read it, but it'll say 250,000 experts active in the community. And I did a bit of digging for a couple of the sites, certainly not all of them, and I discovered that in at least a couple of instances, what's happened is that they've actually gone to a scientific society, bought the membership database, run a Perl script over the top of it to auto-create profiles. So they're not real people, at least in some of the sites. Okay, I'm going to move away from the slides for a little bit and just talk freely. So I'm sure it's obvious to pretty much every person in the room what's going on. I've already kind of alluded to it. But just to state the obvious, you might think that, say, the quickie is the best idea since sliced bread. Let's assume that you think that, even if you think it sounds terrible. Let's assume that you think that. But particularly if you're a young scientist, what are you going to do? Are you going to take you want to get a job, you want to get all these grant support, all these kinds of things. Are you going to take, say, 200 hours in the coming year and spend that time writing, say, a couple of mediocre scientific papers that nobody's ever going to read? Or are you going to take the same time and might make a long slew of really brilliant contributions to the Wiki? Well, which one is going to do more for your career? It is pretty clear which one is going to do more for your career, independent of how scientifically valuable you might think it is. So it is very hard to ask a person to spend their time doing that. Right? Very hard thing indeed. Now, if you look at, say, a project like the Polymath Project or Galaxy Zoo, you might say, well, doesn't that avoid some of these problems? Actually, no. It suffers from exactly the same problem in some sense, or it illustrates the flip side, right? These are projects whose ultimate output is really scientific papers. The Polymath started with a discussion of, questions around authorship and final scientific paper, and at the end of the day, they wrote a couple of scientific papers. Galaxy Zoo has been used to write more than 20 scientific papers. So in some sense, they're using an unconventional means to a conventional end. And that's great. I think these projects are terrific, obviously, but they do have that kind of conservatism about them. They don't have the same nature as the Wiki or one of the other science wikis or one of the scientific social networks, where contribution is purely an end in itself. And so we have this kind of constraint. While the incentive system, while the reward system in science remains the way it is, very oriented towards papers and grants, it is very hard to break that kind of a cycle. I should say, a few people might be thinking, well, how does Math Overflow and similar sites fit into this? Actually, was that why you were raising your hand, out of curiosity?
No, I was just wondering whether it's not the paper so much, but the issue at the end of it is credit, right?
Yeah, that's right.
And how do you...
Papers are a proxy for credit.
Right. How do you get credit for having contributed something in a world where people want to measure your contributions?
That's right. That's right. And that's why, of course...
That's why it doesn't matter for people who are not professionals. In fact,
that's why we have this strange situation where people are absolutely delighted to spend time on Galaxy Zoo, but yeah, exactly. Well, yeah, you're spot on, and I guess I'll come back and explore that. I should say, to some extent, Math Overflow actually avoids this, and that's a point I might come back to later. That's a really interesting point, but it's a bit beyond the scope right now. Okay, so if you want to talk about changing this culture, changing the incentives, changing what people are rewarded for, that seems like a really hard thing to do. How do you get everybody to agree to change simultaneously? Well, that seems impossible. But I want to tell you about two cases where it has actually happened. So the first involves, in fact, the Human Genome Project. Are there any biologists here? Okay. So early 1990s, it is becoming clear, it is clear to many biologists, that the human genome is going to be sequenced sooner rather than later. And there are some interesting discussions going on about data sharing. Now, if you just think sort of naively about the situation, if you're a young biologist thinking about sequencing part of the human genome, what are you going to do with the data? Are you going to upload it to GenBank or one of the other public databases? Right, which is a little bit like contributing to the Wiki. It's not something you necessarily directly get credit for. Or, are you going to keep it to yourself? And of course, a lot of people, everybody can see that at some level this is a question, is a problem. So, well, there's a long story about how we got to the current state, but I want to highlight one particular part of this story, a crucial part that occurred in 1996. There was a meeting held in Bermuda, sponsored by the Wellcome Trust, and in attendance were many of the leading people involved in the Human Genome Project. Craig Venter, who would later lead the private effort to sequence the genome, was present. There were people there from the NIH, from the Wellcome Trust, and they talked this problem over for several days. And they drafted a set of principles, now known as the Bermuda Principles, which state essentially that anybody who took substantial amounts of genetic data should upload those data to GenBank or a similar site within 24 hours, and the data would be put into the public domain. Right? Furthermore, within 12 months, back at the grant agencies, those principles were baked into policy. And that meant that if you wanted to participate in the effort, if you wanted to get money to work on the human genome, you needed to agree to abide by those principles. And in 2000, Clinton and Blair issued a joint statement praising, they don't actually name them by name, but they praise essentially the Bermuda Principles and urge that every country in the world adopt similar principles. So by changing the funding game, they were able to get people to collectively agree to share data very, very early in the whole process. As I say, the actual, there's a long story, and that's merely part of the story, but that's definitely a crucial element. And that's a nice story, but even if you just look at other parts of biology, other types of genetic information, the situation is far from as nice, as open. One biologist of my acquaintance made the comment to me after a talk that he'd been, quote, sitting on a genome for an entire species for more than a year. So that's an entire species of life. Interesting fact, when I tell this to scientific audiences, they tend not to respond. They just kind of think, okay, yeah, well, that's not surprising. When I tell that to public audiences, they're horrified by this fact. That was publicly paid for. What's he doing sitting on it? Interesting fact. Okay, so that's an example where we've moved towards a more open scientific system. I want to go back to a much, much bigger example of change. It's a change that every person in this room, in fact, arguably every person in the world has benefited from. Go back to 1610. So Galileo has just built his first astronomical telescopes. The morning of July 25th, 1610, Galileo points his telescope for the first time at Saturn. And what he's expecting to see, based on his past observations of planets, is that it's a little disk. And he's surprised, because sure, he sees a little disk, but on either side, he sees little bumps, right? And what he's seeing is what we now know was in fact the first ever hint of the rings of Saturn. So does he disclose this to the whole world? Does he announce it? No. What he does is he writes down a description of the discovery in his private working notes, and then he scrambles the letters into an anagram, and within 24 hours he mails off that anagram to 4 of his astronomer colleagues, including the great astronomer Kepler. And this means that if somebody else, say Kepler, later makes the same discovery, Galileo can reveal the anagram and still get the credit, but in the meantime, he hasn't revealed anything at all. Imagine the human genome had been revealed as an anagram. Right? Not so good. Not so good. Okay. So, see how I'm doing for time. All right. So it'd be nice to say that Galileo is a bad guy. But actually, this wasn't uncommon at the time. There was little incentive for people to share this kind of information at the time. So Leonardo did the same thing. Huygens did the same thing. Newton did the same thing. Robert Hooke revealed Hooke's law, which you may remember from high school physics, in the form of an anagram. Very common type of a behaviour at the time. And so scientists will say, oh, well, we solved this problem. We invented scientific journals. Okay? That's a one sentence that actually captures a huge piece of history and a real battle at the time. Because people didn't want to adopt the scientific journals. They didn't rush out madly and start publishing. No, they had to be dragged kicking and screaming into it, and they would complain, it takes too much time, I don't want to do this, why would I reveal stuff to my competitors, etc., etc., etc. All the same things that we see today, but now for the scientific journal. And so here's how Mary Bowers Hall, who was the biographer of Henry Oldenburg, the editor of the first serious scientific journal, the Philosophical Transactions, here's how she describes what Oldenburg had to do. Oldenburg would, quote, beg for information, sometimes writing simultaneously to 2 competing scientists on the grounds that it would be best to tell A what B was doing and vice versa, in the hope of stimulating both men at the time, to more work and more openness. She has these they're terrible examples of Oldenburg figuring out 2 people working on the same problem, kind of right to one, insinuating that the other was a little bit ahead of where they really were at, to try and get them, to disclose kind of to say, oh, I can do that too, and here's how. We kind of bounced these letters backwards and forwards and published distillations of them in the journal. Right? Pretty interesting kind of a situation. Here's Elizabeth Eisenstein, one of the great scholars of the printing press. She's talking, I should say. She has this wonderful book about the printing press. She has a chapter about science. She's kind of talked and talked and talked about all these amazing things people are doing with the printing press. Then in the chapter about science, she's like, and what on earth were the scientists doing? She's befuddled by it. Exploitation of the mass medium, books, was more common among pseudoscientists and quacks, sounds like wikis today, than among Latin-writing professional scientists who often withheld their work from the press. Well, this is 220 years after Gutenberg, right? It's easy to forget that. It's not next week, it's not even next century. It's more than 2 centuries after, and scientists don't want to publish their work. That's the period she's talking about. And so the easy answer is to say, well, what caused the change to the system we take for granted today was that we established this link that we all take for granted. We all just assume that there's a link between publication and career success, the link I've been talking about so much today. But actually establishing that link, causing that transition, took decades. Some historians have called this an open science revolution. And so there's a historian at Stanford named Paul David who has written a very nice 110-page paper studying how this occurred. And to do his paper a grave injustice and sum it up in 2 words, patron pressure is his explanation. So what do I mean by that? I'll tell you a little story. It's actually mine, it's not his, but I think I hope he would agree. It concerns an earlier discovery of Galileo's prior to the rings of Saturn. It was Galileo's first really big discovery. It was of the 4 Galilean moons of Jupiter. I should say, by the way, just for context, it's easy to think, what was going on? These were not big things. How come we're so excited about this? But of course, at the time, these were huge discoveries. Our view of the heavens had not changed since ancient times. So it was amazing. Galileo became famous all over Europe because of this discovery. And the reason he became famous is because he published it essentially immediately. Here is the pamphlet. And take a look at the fonts here, right? Siderius Nuncius, the Starry Messenger. Title, big font. Not so surprising. Galileo's name, pretty big font. What's most visible? Medicia Sidera. Galileo immediately made the discovery, wrote to potential patrons, including the Medici family, and said, I will name these moons after you if you agree to become my patrons. That's why we see that. Too bad for the Medici, we now call them the Galilean moons. Guess you can't have it all. And of course, the key point here is that funders, patrons, often have much more incentive for openness than scientists do. They have different incentives. The Medici wanted this to be known. Galileo was maybe a little bit more ambivalent, but to get their money, he was willing to go along. And that is potentially what caused that open science revolution. So let's move forward in time to today to talk about achieving some of the kinds of changes. Let's assume that you agree with me now, I hope, that some such change is needed. People often say, well, how do you solve the problem? Like, what's the one thing you can do? I think that's the wrong way to think. There's certainly no single silver bullet, many small, tiny little steps. And I'll talk just a little bit about a few of those steps. I want to come back to the genome again, and I want to draw your attention to a parallel with the Galileo story. The genome is open, at least in part, because of funder pressure, as we saw. That kind of story involving the Bermuda Principles. Right? Very similar kind of a story to Galileo and the moons of Jupiter at some level. You have this enforcement mechanism. That's important. And so I would say that more broadly, grant agencies should work towards stronger open data policies than they currently have. Many of the funders do, of course, have open data policies. I'm sure many of you have been impacted by the NSF's changes in that respect this year. That's a very big move. Towards a broader range of data, and certainly much earlier in the discovery process. I think they should also work towards open code policies, and in particular, incentivize the use of new tools by encouraging scientists to submit non-standard evidence of impact. What do I mean by that? I mean, if people want to use contributions to sites like the Wiki as evidence of impact, that should be fine. Or if, for example, I worked in an atomic physics lab for a while. I'm not actually an atomic physicist, but I was surrounded by them. And there's a lot of things, a lot of types of knowledge that they have that is very hard to describe in a paper, but it's important scientific knowledge, but it's easy to show in a video. And so you can take videos and upload it maybe to YouTube, or there's actually a journal, the Journal of Visualized Experiments, that will send a camera crew into your lab, take a video of you explaining how you do something, and that's the kind of thing that there needs to be more of and which can be used legitimately as a kind of evidence of scientific impact. Or of code, or of data. Actually, this is an example I particularly like. This is a scientist in Berlin who's been studying fruit fly trajectories under different conditions, does all kinds of terrible things to these fruit flies, and uploads the data essentially in real time. Right, so you can track it pretty much right at the instant that they're actually doing the experiments. So just, that's, I guess, partially a rhetorical question, but why is a curriculum vitae with 30 papers and no code acceptable, indeed even encouraged, while a CV with no papers and 30 code repositories containing valuable scientific knowledge is not? I think we all take for granted that this is the way things are, but if you were designing the scientific system from scratch, it's not necessarily so obvious what the answer to that question is. And certainly a very simple thing that can be done by many people is just to add one extra line to grant guidelines or to job descriptions. Applicants are encouraged to submit non-standard evidence of impact, videos, code, research blogging, whatever. I would go so far as to say, I think as a broad general principle, that in fact publicly funded science should be open science. I'll be done in just a couple of minutes. There are certainly some exceptions to this. There need to be exceptions for confidential and proprietary knowledge, but we can move the fulcrum over. We can really, there's so much knowledge wrapped up inside people's heads and in their laboratories that can be moved out and moved onto the network where it can do some good. So as a broad general principle to work towards, I think this is well worth doing. So obviously I think that people in a position to affect job descriptions and grant policy should do so, but of course that's not most people. It's probably not most people in this room. What about the rest of us? Well, just as a simple basic thing, everybody can do at least a little work in the open if they're so moved, if they think this is worth working towards. They can upload some of their code. They can do as this person did and upload some of their data. Something I've done quite a bit of is research blogging. Actually, I'm kind of proud of this. This is a series of posts I wrote about a technical topic, fermions and the Jordan-Wigner transform. For whatever reason, I have no idea why, I've had tens of thousands of downloads of this. I get a lot of Google hits. It has a surprising amount of impact. And they can start to cite non-standard contributions. Here's just an example, a blog post by Martin Fenner about how to formally cite a blog post. I'm hoping that tools like Google Scholar, Microsoft Academic Search will at least start considering using non-standard contributions, things like code repositories, things like blogs, potentially in their statistics. When people are doing serious research blogging, for example, maybe it shouldn't necessarily have the same status as a paper, but there's an interesting conversation to be had about how it should show up in people's scholarly record and in statistics about their impact. And the last thing to do, of course, is once you do it, brag about it. So this is Steve Cook, an open notebook scientist working at the University of New Mexico, and he prepared his tenure document in part in the open, and he shared it with lots of people, and one of the things he did, he was great. He has a long, long list of ways in which he's sharing knowledge in the open, all kinds of stuff. YouTube videos, data sets, collaborations caused as a result of this kind of sharing. So he's bragging about it, and that's terrific. So there are all these kinds of small steps, which I think ultimately, if enough people participate, will start to build unstoppable momentum towards a much more open and far more effective scientific system. I will just finish with one, it's kind of a Steve Jobs, one more thing at some level. It really is. It's a bit of a break, but I want to mention this because I think it's important. The White House has out at the moment a request for information on public access to research. And so they've got, I think it's a list of 8 questions, which they're inviting comment on. A lot of it's related to the issues that I've discussed today, and they're inviting input by January the 2nd. Kind of a similar thing, this is an act, the Federal Public Research Access Act, that would take all research output, all papers produced by US federal agencies with their funding of over $100 million a year, and enforce an open access policy on it. What that would mean is that within 12 months of being published, it would go into some kind of an open access repository. So this this act has come out, I think in 2006 and 2010 into Congress. It's been sent back into committee. I'm reasonably hopeful that it will come back, it will be considered by Congress again in the near future. An organisation that's doing a lot of good things with both of these is the Alliance for Taxpayer Access, and they have more information about things that people can do online if you're so moved to contribute. And with that, I will say thank you.